Sunspot region AR40446 has now achieved beta-gamma magnetic complexity, confirmed by NOAA's GOES-19 SUVI instrument as of this morning, May 28, 2026, making it the single most magnetically unstable active region on the entire Earth-facing solar disk, and it is aimed directly at the South Pacific. In the 72 hours since it first rotated into view on May 23rd, this region has fired 16 C-class flares, then a C9. 7 blast at 1238 UTC on May 26th that came within a fraction of a unit of breaching the threshold into M-class territory, and now, as a high-speed coronal hole solar wind stream presses against Earth's magnetosphere on this date, the conditions for an X-class eruption are not hypothetical. They are documented in the instrument record. The question is not whether AR4446 can produce an X-class flare. The question is when, and whether the South Pacific is still in its line of fire when it does. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every time a region like AR4446 appears on the solar disk, and the instruments begin reading what they are reading right now, the people who need this information most are the last to receive it. That is the gap this channel exists to close. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, the GOES-19 SUVI and XRS instruments, NASA's Solar Dynamics Observatory, the Smithsonian Global Volcanism Program, where relevant and peer-reviewed research on solar cycle behavior and geomagnetic storm impacts. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us. But that is not even the complete picture, because what the instruments are recording around AR4446 today is not simply a story about one dangerous sunspot. It is a story about the convergence of multiple solar systems arriving simultaneously at a single point in time, and the region of Earth sitting in the geometric crossfire of that convergence is one of the most communications-dependent, aviation-dense, and emergency response-fragile corridors on the planet. The South Pacific, the vast oceanic domain stretching from the eastern coast of Australia across to French Polynesia, encompassing New Zealand, Fiji, Tonga, Samoa, Papua New Guinea, and the aviation corridors connecting them to Asia, the Americas, and the rest of the world, runs almost entirely on high-frequency radio communication. HF radio, the very band that an X-class solar flare attacks first, most completely, and most suddenly. What is accumulating above the South Pacific right now is not a weather event in the conventional sense. It is a space weather event with terrestrial consequences that are immediate, measurable, and, in some scenarios, life-threatening. And it is building on a timeline measured in hours, not days. To understand exactly what AR4446 represents, it is necessary to understand the language that solar physicists use when they describe magnetic complexity in a sunspot region, because scientists choose their language carefully here, and that careful language is itself the warning. A simple sunspot has what is called an alpha configuration. Two adjacent spots of opposing polarity produce a beta configuration. When a third polarity intrudes into the same penumbral boundary, the region is classified beta-gamma. And when the opposing polarities are so deeply intermingled that they share a single umbral boundary, the technical designation is beta-gamma delta, the region is considered capable of producing the most powerful flares the Sun can generate. AR4446 crossed into beta-gamma territory on May 26th. As of this morning, solar observers are monitoring whether a delta component is forming in the region's southern umbral boundary. The 10 7-centimeter solar radio flux, a proxy for overall solar activity, stood at 139 solar flux units as of May 27th, significantly elevated above baseline, confirming that the solar disk as a whole is in a heightened state of energetic output. AR4446 is not operating in isolation. It is operating on a solar disk that is already running hot. Here's where this account becomes genuinely significant. AR4446 did not emerge quietly. When it first rotated into view at the Sun's eastern limb on May 23rd, it announced its arrival with 16 C-class flares in a single 24-hour period. 16. In isolation, C-class flares are relatively minor. They produce brief, localized ionization in the upper atmosphere and minimal disruption at the surface. But 16 of them in one day from a single active region is not routine behavior. It is the fingerprint of a magnetic system that is under extreme internal stress, releasing energy in rapid-fire bursts because the field lines threading through its sunspot cluster cannot find a stable configuration. Think of it this way. Imagine compressing a spring not once, but continuously, and instead of the spring releasing in a single catastrophic uncoiling, it releases in a series of sharp metallic snaps, each snap smaller than the full release would be, but each snap telling you unmistakably that the coil is still under load. AR4446 has been snapping since the day it appeared, and it is not released. The C9-7 flare at 12:38 UTC on May 26 was the most significant of those snaps so far. C9-7 does not simply mean a large C-class flare. It means the event measured 7 times 10 to the power of minus 6 watts per square meter in the 0, 1 to 0. 8 nanometer soft X-ray band as detected by the GOES-19XRS instrument. The M-class threshold begins at 10 to the power of minus 5 watts per square meter. AR4446 is C9. 7 blast was separated from M-class intensity by less than 3% in measured output. 3%. In solar flare terms, that gap is not a safety margin. It is a rounding error in a system that can shift by a factor of 10 in the time it takes the sun to rotate 3 degrees. And the region is still on the Earth-facing disk. It is not rotated away. It is not winding down. It is evolving. Now add the second factor present on this date, the coronal hole. A large equatorial coronal hole on the solar disk has been streaming fast solar wind toward Earth's position since May 26, and that stream is arriving now on May 27th and 28th. Coronal hole streams carry solar wind speeds that can reach 700 kilometers per second. That is 700 kilometers every single second. Not per hour, per second. The stream from this particular coronal hole is expected to produce unsettled to active geomagnetic conditions throughout today, with forecasters at the Space Weather Prediction Center noting a slight chance of isolated G1, minor geomagnetic storm, intervals developing. Under normal circumstances, a G1 watch is a relatively modest alert, but these are not normal circumstances. When a high-speed solar wind stream arrives at Earth's magnetosphere at the same moment that an AR4446 class region is in the process of escalating toward X-class flare potential, the two phenomena interact. The compressed magnetopause, the boundary between Earth's magnetic field and the solar wind, becomes more sensitive to additional magnetic perturbation from a coronal mass ejection. The threshold for a significant geomagnetic storm drops. The system's tolerance for further energetic input narrows. What would ordinarily be a manageable event becomes the trigger for something larger. And there is a third factor that most coverage of AR4446 has not yet fully addressed: the far side. On May 25th, NOAA's GOES-19 satellite, specifically its CCOR-1 coronagraph instrument, captured a coronal mass ejection erupting from an unseen active region on the far side of the Sun. That far side region is not visible from Earth-based instruments, but its magnetic signature is detectable, and multiple solar observers noted as of May 26 that the activity level behind the Sun's northeast limb suggests the possible return of former active region AR4432, a region that completed a backside transit and may be rotating back into Earth view within the coming days. If AR4432 returns in a state of elevated complexity, similar to what it showed before it rotated away, the South Pacific will find itself facing not one threatening sunspot, but two, arriving on the disk within days of each other during a period when the solar wind baseline is already elevated. The system is not inactive, it is accumulating. This is not a hypothesis. This is documented in the geological and instrumental record, and the record makes one fact absolutely clear. What our 4446 is doing right now, other regions have done before, and when they completed the process they began, the results were not theoretical. They were catastrophic. The year was 2024. The month was May. The active region was our 3664, and what it produced in the space of 4 days rewrote the contemporary understanding of geomagnetic storm risk. Beginning on May 8th, our 366 for a region that also carried beta-gamma-delta magnetic complexity began firing X-class flares in sequence: X1, 0, X2, 25, X1, 12, X3, 98, and finally, as the region rotated toward the western limb on May 14th, an X8. 7, the most powerful solar flare recorded in solar cycle 25 and the most powerful eruption detected since November 2003. The resulting geomagnetic storm reached G5, the maximum level on NOAA's 5-point scale. The KP index hit 9, the disturbance storm time index, the DST, plunged to negative 412 nanoteslas, a number that places the May 2024 event among the most severe geomagnetic storms of the modern satellite era. The solar wind speed reached 950 kilometers per second during the peak. The interplanetary magnetic field southward component reached negative 50 nanoteslas, aligning perfectly with Earth's magnetic field in the orientation that maximizes energy transfer, the orientation that is the geomagnetic equivalent of a key fitting. Alok, the aurora was visible from Florida, from Texas, from the Caribbean, from latitudes that had not seen the northern lights in living memory. Power grid operators across North America, Europe, and Australia spent 48 hours in emergency mode. Satellite operators maneuvered assets to defensive configurations, and the world was reminded with shocking clarity that the sun does not issue warnings. It issues events. R4446 is not R3664, not yet. But R3664 also began with elevated C-class activity before it began its X-class sequence. The path from where R4446 stands today to where R3664 stood at peak intensity is not a long one on the scale of solar flare physics. It is a question of whether the magnetic field lines threading through R4446E's penumbral boundary find their catastrophic reconnection point before the region rotates off the Earth-facing disk or while it is still pointed directly at the South Pacific. Now bring this back to the people. Bring it back to the specific. Human beings who live and work in the path of what the instruments are describing. Consider the 930,000 people of Fiji, the island archipelago of 333 islands spread across 194,000 square kilometers of ocean, whose aviation authority coordinates flight safety using HF radio communications that would be rendered completely inoperable within 8 minutes of an X-class flare impacting the sunlit side of the Pacific. 8 minutes. That is the travel time of the electromagnetic radiation from the sun to Earth at the speed of light. There is no warning, there is no countdown. The flare peaks, 8 minutes pass, and the ionosphere above the South Pacific is transformed from a radio-reflective layer that bounces HF signals across oceanic distances into a radio-absorbing wall of ionized plasma that swallows those signals completely. Every aircraft flying over the Central Pacific at the moment of impact and at any given hour, there are between 50 and 80 commercial flights transiting that corridor loses HF radio contact with ground control. The pilots do not lose the ability to fly, but they lose the primary backup communication system that underpins all oceanic flight safety protocols, the system that exists precisely for the moments when satellite communication fails. And X-class flares frequently degrade satellite systems at the same time they destroy HF radio. The redundancy disappears simultaneously. It has already happened once, and the record of it is still preserved in aviation incident reports from the 2003 Halloween solar storms, from the X-28 class eruption of November 4, 2003, which produced the strongest measured flare in the modern instrumental record and blacked out HF communications across the Pacific for hours, forcing air traffic control centers to implement emergency separation protocols for every flight over open ocean. There are also the 100,000 people of Tonga, the Pacific Island Kingdom sitting 1,750 kilometers northeast of New Zealand, where the National Emergency Management System runs on HF radio because no cable infrastructure connects the outer islands to the capital Nuku'alofa. When Tonga's Hunga Hapapai volcano erupted in January 2022, the communication blackout that followed the eruption, a blackout caused by the physical severing of the undersea cable, demonstrated in brutal precision what loss of radio contact means for a Pacific Island nation in crisis. The outside world did not know the full scope of what had happened for nearly 24 hours. A major X-class solar flare impacting the South Pacific during a volcanic emergency, a tsunami warning, or a tropical cyclone response would replicate that blackout not for 24 hours, but for the duration of the flare's impact on the ionosphere, which for an X-class event can run from 30 minutes to several hours depending on flare intensity and duration. Minutes are not hours, and in this context, that difference is everything. Return now to the science. Because what makes the current situation around R4446 genuinely alarming is not just the magnetic complexity of the sunspot itself, it is the interaction between that complexity and two connected global systems that amplify risk in ways that are rarely communicated to the public. The first is the state of solar cycle 25. The sun operates on an approximately 11-year cycle of activity, moving from solar minimum when the disk is largely quiet and spotless to solar maximum. When active regions multiply, flares become frequent, and coronal mass ejections increase in both frequency and intensity. Solar cycle 25 reached its maximum in late 2024 and early 2025. The prediction from NOAA and NASA was for a moderate cycle, but cycle 25 exceeded those predictions significantly. The X8, May 7, 2024, and the extraordinary multi-X class barrage of early February 2026, when the sun produced an X8, 1, an X2, 8, an X1, 0, and an X1, 6 within a 24-hour period, confirmed that cycle 25 was not behaving as a moderate cycle. It was behaving as one of the more energetic cycles of the modern era. The 7 centimeter radio flux reading of 139 solar flux units recorded on May 27, 2026 is consistent with a solar disk that is post-maximum but far from quiet, a disk in what researchers describe as the declining phase of elevated activity, where large, complex active regions continue to emerge with regularity even as the overall cycle trends downward. R4446 is not a remnant of a dying cycle. It is a product of a cycle that has not yet finished demonstrating its full range. The second connected system is the geomagnetic baseline established by the coronal hole stream now arriving at Earth on May 28. When solar wind compresses Earth's magnetosphere, the invisible magnetic shield that deflects charged particles from the solar wind and from cosmic sources, it alters the conditions under which a subsequent coronal mass ejection would interact with the planet. A magnetosphere that is already under elevated solar wind pressure is more susceptible to the southward-directed magnetic field within a CME's internal structure. This is the B's parameter, the Z component of the interplanetary magnetic field, and it is arguably the single most important number in space weather impact assessment. During the May 2024 G5 storm, B's reached negative 50 nanoteslas. That southward orientation allowed the CME's magnetic field to reconnect with Earth's own field at the dayside magnetopause, punching energy into the magnetosphere in a cascade that drove the KP index to 9 and the DST to negative 412. If our 4446 produces an X-class flare and an associated full halo CME within the next 24 to 48 hours, while the coronal hole stream is still elevating the solar wind pressure at Earth's magnetopause, the arriving CME would encounter a pre-stressed magnetospheric environment. The threshold between a G2 storm and a G4 storm in such conditions is not the CME's initial energy, it is the B's orientation at the moment of impact, and B's cannot be measured reliably until the CME reaches the L1 Lagrange point, approximately 1.5 million kilometers from Earth, roughly 15 to 60 minutes before impact, depending on CME velocity, 15 to 60 minutes. That is the operational warning window for the South Pacific's aviation system, maritime network, emergency communication infrastructure, and electrical grid operators if a full halo CME from our 4446 departs the Sun today or tomorrow. 15 minutes on the short end, to place that in physical terms, a 747 cruising. At 900 kilometers per hour crosses approximately 225 kilometers in 15 minutes. The oceanic separation between Fiji and New Zealand is 2,780 kilometers. An HF radio blackout affecting that corridor with 15 minutes of warning and lasting 90 minutes would cover multiple aircraft simultaneously in open ocean airspace with no alternative navigation support and degraded satellite uplink. NOAA's space weather follow-on L1 observatory SUFO L1 entered its final orbital position at the Lagrange 1 point on January 23, 2026, providing the most current early warning capability for incoming CMEs. That capability is real and it is significant, but it measures what arrives at L1 after the CME has already traveled 149 million kilometers from the Sun. The physics of the CME's journey do not allow for earlier detection of B's orientation with current technology. What the instruments show at L1 is the first and only true warning before impact. The monitoring is in place and detection is possible, but prediction of impact severity in advance of L1 data is not. There are those who will read this data and conclude that a region carrying beta-gamma complexity producing a near-M flare does not automatically escalate to X-class. That is true. Not every active region with elevated magnetic complexity produces a major eruption. The Sun is not mechanically predictable. Solar flare forecasting remains a probabilistic science, not a deterministic one. What NOAA's SWIP's forecast models indicate for active regions with our 4446E's current profile is an X-class flare probability in the range of 20 to 35% over any given 24-hour window, depending on the continued rate of magnetic flux emergence in the region's penumbral boundary, 20 to 35%. That number deserves translation into human terms. A 35% probability of a major X-class solar flare in 24 hours is higher than the probability of rain on any given afternoon in London during the month of August. It is nearly identical to the probability assigned to moderate earthquake activity in the Cascadia subduction zone on any given day. It is a probability that, in the domain of aviation safety risk assessment, would ground flights. It would not in the domain of space weather, because the protocols for space weather response do not yet carry the same operational weight as those for other hazard categories. That gap between the probability assigned to the hazard and the institutional response to it is itself a story that belongs in this account. Think now of New Zealand, 5 million people. A nation whose southern Alps generate extraordinary radio propagation conditions, whose coastline runs 15,000 kilometers in a configuration that makes it uniquely dependent on maritime HF communications, and whose geographic isolation in the southwestern Pacific places it at the intersection of every major oceanic communication corridor between Australia, South America, and Antarctica. The New Zealand Antarctic Research Program Scott Base and the logistics chain supporting it runs on HF communication during the polar months when satellite windows are limited. A major X-class flare impacting the South Pacific during the austral winter would degrade those communications at the moment they are most critical. The people at Scott Base would not be in danger, they have redundant systems and trained operators, but the example illustrates the geography of vulnerability that the South Pacific represents in the context of extreme space weather. Isolation is not an abstraction here, it is a measurement in kilometers of open ocean between one communications node and the next. The Carrington event of September 1859 is the benchmark against which all subsequent geomagnetic storms are measured, and what it demonstrated in an era of telegraph lines and no satellites, no HF radio, no GPS, no aviation was that the Sun is capable of generating a geomagnetic storm of sufficient intensity to drive induced ground currents powerful enough to set telegraph offices on fire. The estimated X-ray flux of the Carrington flare has been retrospectively assessed at approximately X45 or stronger, well beyond the X28 of 2003, which itself caused spacecraft anomalies, forced operators to switch instruments to safe mode, and produced radio blackouts lasting hours, a Carrington equivalent event. In 2026 would not set telegraph offices on fire. there are no telegraph offices. It would instead overload long-distance power transmission lines, saturate protective relaying equipment in electrical grid substations, degrade GPS signals for days, and produce induced currents in undersea cables capable of permanently damaging the fiber optic amplifiers that carry the internet traffic of entire continents. The economic modeling for a Carrington-class event applied to the modern grid has been conducted by Lloyd's of London, the Cambridge Centre for Risk Studies, and multiple governmental agencies. The estimates converge on infrastructure damage in the range of $600 billion to $6 trillion for North America alone. The South Pacific is not North America, but it is connected to every global system that North America's infrastructure supports. The internet does not stop at oceanic boundaries. Our 4446 is not producing a Carrington event. What the data shows is a region carrying beta-gamma complexity, a near M-class eruptive history over 5 days, an active coronal hole stream compressing Earth's magnetosphere today, and a far-side region with unknown current status, potentially rotating back into view within days. What the data shows is a probability window, a 24 to 48-hour period during which the Earth-facing orientation of R 4446, combined with the elevated solar wind baseline, creates a higher than background risk of an X-class flare impacting the South Pacific side of the dayside ionosphere. That risk is real. It is documented in the official instrument record. It has a named probability range assigned to it by NOAA's forecasters. And it exists in a part of the world where the gap between the scientific community's awareness of the threat and the public's awareness of it is measured not in data points but in the simple absence of coverage, the absence of the kind of sustained, precise, data-grounded communication that turns a probability percentage into something a person in Suva or in Auckland or in Port Moresby can actually understand and act on. Because the people of Suva, Fiji, deserve to know that the sunspot region currently aimed at their corner of the world is the most complex active region on the Earth-facing solar disk. The 930,000 Fijians who rely on aviation links for medical evacuations, the fishermen and mariners whose HF radio sets are the only communications technology that functions reliably across open water, the civil aviation controllers at Nadi International Airport who manage the Pacific's second busiest oceanic crossing corridor, they deserve the same quality of information that a solar physicist in Boulder, Colorado receives at 6 o'clock UTC when NOAA's Morning Space Weather Bulletin lands in their inbox. The instruments are showing something on May 28, 2026. They are showing a beta-gamma sunspot region at the peak of its Earth-facing orientation. They are showing a high-speed solar wind stream already pressing against the magnetopause. They are showing a solar disk with an elevated 10.7 centimeter radio flux. They are showing a 35% probability window for an X-class event within 24 hours, with a dayside impact zone centered on the South Pacific when the region fires. This is not a hypothesis. This is documented in the current instrument record. And what the record of every previous solar maximum has confirmed from 1989, when a G5 storm collapsed the hydro power grid in 92 seconds and left 6 million Canadians without electricity for 9 hours, to 2024, when our 3664 demonstrated that the modern grid's vulnerability is not a historical artifact but a present-day engineering reality, is that the probability window is not a comfort, it is a countdown. Our 4446 has not yet produced its defining eruption. The beta-gamma configuration is holding, the magnetic flux is still accumulating. The flare that our 4446 is building toward, if it comes, when it comes, will travel 149 million kilometers at the speed of light and arrive at Earth's ionosphere in 8 minutes and 20 seconds. The coronal mass ejection associated with it, if the eruption launches one toward Earth, will arrive between 15 and 72 hours after that, depending on its initial velocity, bringing with it the magnetic field orientation that will determine whether the South Pacific experiences a radio blackout lasting 30 minutes or a geomagnetic storm lasting 3 days. The monitoring systems are in place. The L1 observatory is operational. The forecast centers are watching, and none of that changes the fundamental, unalterable fact that the sun does not negotiate its timeline with the instruments designed to observe it.